How does kinetic energy become relativistic? Imagine you are in a race where your speed keeps increasing. As you run faster and faster, nearing the speed of light, something strange happens to your energy. That's when classical ideas about motion start to break down. At everyday speeds, we use a simple formula to find kinetic energy, which is half of the mass times the velocity squared. But when speeds get close to the speed of light, this formula no longer works. Instead, Einstein's theory of special relativity comes into play, changing how we understand energy and motion. In relativistic physics, an object's total energy includes both its rest energy and its kinetic energy. Rest energy is the energy an object has just because it has mass, and it's calculated by multiplying the mass by the speed of light squared. When an object moves very fast, its total energy is given by a more complex formula involving a factor called the Lorentz factor. This factor depends on how close the speed is to the speed of light and increases dramatically as the speed gets nearer to it. This Lorentz factor is written as 1 divided by the square root of 1 minus the velocity squared divided by the speed of light squared. As the velocity approaches the speed of light, this denominator gets smaller, making the Lorentz factor grow larger and larger. Because of this, the total energy of the object increases without limit. The relativistic kinetic energy is then found by subtracting the rest energy from the total energy. At low speeds, the Lorentz factor is close to 1, so the relativistic formula simplifies to the classical one. But at high speeds, the Lorentz factor becomes very large, and the kinetic energy increases much faster than the classical prediction. This means that as an object with mass gets closer to the speed of light, it takes more and more energy to keep accelerating it. In fact, it would requiring an infinite amount of energy to reach the speed of light itself, which makes it impossible for any object with mass to do so. Understanding this transition from classical to relativistic kinetic energy is especially important in fields like particle physics and astrophysics. When particles are accelerated to near light speeds in particle accelerators, their energy calculations must include relativistic effects. Similarly, in space phenomena involving high-speed particles, knowing how kinetic energy becomes relativistic helps scientists accurately describe their behavior. So, in simple terms, kinetic energy becomes relativistic when an object's speed gets very close to the speed of light. At that point, the classical formulas no longer work, and Einstein's equations must be used. This change shows the fundamental limits of how fast objects with mass can go and how energy and motion are connected in our universe.